Outright, I'd like to thank my advisor, Craig Paukert, and project leader, Zach Ford, for their support. As you've heard a lot this morning, electrofishing is a common and cost-effective method for estimating important population metrics like relative abundance and size structure. And a common index of abundance catch per unit of effort has a challenging assumption that catchability, or the probability of capturing a fish given when it's present, is fixed between and within sampling events. A lot of factors can influence this estimate of catchability, and sources of bias are poorly understood. On top of this, as you've heard, Blue Catfish and Flathead Catfish have a unique response to low-frequency electrofishing. They service great distances from the boat. There's a time component. And so although we don't understand all the factors currently influencing catchability in our relative abundance estimates, many agencies are adapting some sort of standard protocols to kind of hold some of these unknown biases constant to make comparisons across space and time. This is a catch equation in your sample. It's the product of the true population catchability, and assume that the amount of effort that you expend will increase catch. Here's slightly rearranged, and as you can see, a lot of factors can influence our estimates of catchability, and although it seems daunting, in some form or another, it could be argued that most of these can be addressed in some form in standard sampling protocols. Perhaps what would be difficult is fish size in a system and stream morphology or lake morphology. My research is the second phase of a 6-year electrofishing project between the University of Missouri and the Missouri Department of Conservation. And the first phase of the study, in a controlled laboratory environment, they sought to determine the effective connectivity of blue catfish and flathead catfish, which is useful for developing species-specific power goals, and then to determine the field intensity that's necessary to elicit 3 capture-prone responses: twitch, electrotaxis, and immobilization. And then provide those recommendations to the second phase of the project, where we sought to validate some of these results and recommendations in a field setting. Specifically, my research was to evaluate the catchability in a field setting of blue catfish, flathead catfish, based on fish size, species, and water temperature, using 2 recommended waveforms at 2 different power levels. The 2 waveforms that are recommended, there's a commonly used waveform, 15 pulses per second, 30% duty cycle, which also in the laboratory trials had the least length bias. And then the second waveform that we tried, about half the frequency of the common waveform, was 810, that's what I'll refer to as. And in this waveform in the laboratory we used because it produced an aggressive twitch response in flathead catfish, and so we thought that these would be a good comparison. So to estimate the catchability, you need known numbers and sizes of fish. And although we considered doing mark and recapture experiments in large rivers and reservoirs, we thought that these models would be confounded with either disparities in fish population density or habitat, or just variation in water levels and flows. And so fortunately, the MDC has 20 1.5 acre experimental ponds located outside of Columbia that were readily available for our use. These ponds are about 8 feet deep and they taper up, but we can drain them, we can fill them up, and they're about 1/2 acre in size. So we collected fish all across the state with jug lines, hoop nets, and low-frequency electrofishing, and brought them into those ponds where we stocked a known species, number, and size group of fish in those ponds, as well as with bait fish. We went off, we consulted with some hatchery managers and used some guidelines that Texas Parks and Wildlife put out for stocking densities in ponds of broodstock blue catfish, and it was about, for our ponds, it ended up being about 500 pounds per acre. So luckily that kind of teased out to be about 100 stocked preferred length fish, or 25 preferred length and larger, and that was the cutoff for our 2 size groups. Here's an aerial, like a drone picture of the ponds. That's half the ponds below Little Dixie Lake. So once we had suitable numbers of fish to conduct our trials, we anchored a boat near the deepest third of the pond. We kept the boat stationary throughout the trial to try to maintain a consistent electrical field, and we would alternate our treatments. And so now that you know about the ponds, we decided on the 2 power settings because, as most of you know, blue catfish will come at great distances away from the boat, often even a couple hundred feet. We don't get that in these ponds because they're just a little bit on the small side, and so we had some concerns that we were overpowering fish, or might potentially be overpowering fish, so we reduced the power by 20% for applied voltage, or about 35% for watts. We gave the ponds a 3 to 5 day resting period between sampling events, and then we'd anchor the pond, gently lower some anchors in the boat, get the boat in the pond, and we'd fly a drone about, the average was 175 feet above the trial, And so keeping that boat stationary, we just counted the fish that came up and how long they came up, the distance that they came up, etc., using the drone footage. So we weren't dip netting fish. This is, if anything, it's like a maximum catchability because we don't account for dip netting efficiency. And then we define catchability as the number of fish that surface for greater than 3 seconds per the drained count after the trials when we drain the pond, for that adjusted number of fish throughout a 3-minute trial. Here's just a screenshot of some of the drone footage. It was remarkably stable. It could just GPS spot lock for up to 20-mile-an-hour winds, and it's in 1440p. Those are 2 very large flathead catfish surfacing around the boat during a trial. So this wasn't without challenges, and some of the challenges that we faced in particular was a narrow water temperature window in these small ponds. So while Truman Lake and the Missouri River and these systems that were collecting fish are kind of slow to heat up, the ponds in 2018 we had kind of a hot and dry spring, and so by the time we had adequate numbers of fish out of Truman Lake and out of the Missouri River, our ponds were sitting in the high 80s, approaching 90 degrees, and so we actually elected to kind of hold off shocking them, and to avoid that potentially happening again in the spring, we kept those fish in the pond for the entire year. And so then it became another question of how do we ensure that the fish condition remains good, that water quality is suitable, and how much food do we feed these things. And so we monitored DO when possible, try to evaluate if it was getting below 4 milligrams per liter. It didn't. We treated algae blooms sometimes with Q-Train, and then we just gave them all the fish, the bait fish in the world, to keep them happy. And then last, logistical constraints. So we were limited to the spring and the early summer because in the fall and late summer, I have a catchability study for smallmouth bass in non-wadable rivers in southern Missouri. And then just icing on the cake was, as we were doing a lot of electrical field mapping in the fall, we kind of found that the sealant that they used in those ponds was more conductive than the water. And so we were actually getting some fish and just some test trials that were coming up in adjacent ponds. And so we mapped this out. We bought a literal ton of salt, high-grade salt, made a brine solution, and during the winter we actually bumped the conductivity up to be about, the average was 250 microsiemens, whereas before it was about 100, and it matched the substrate typically. And because of this, we would alternate and skip over ponds as part of our sampling protocol. In total, we transported just over 700 catfish to these ponds, to 10 of the ponds, and we completed 88 trials. We, using the drone footage, kind of squeezed out a little more data with mean distances and surfacing times of the fish, and we also mapped an MDC electrofishing boat, 200 feet in kind of all cardinal directions and diagonals, and we were able to experiment with a big State Fair aquarium tank, as well as some net pen trials that we tried out on Truman Lake. This is the results of draining the pond, so it just kind of shows the condition of the fish after being in those ponds for 1 year. And we had some information to suggest that survival would be high. So you have the groups, the small blues, small flatheads, big flatheads in the group column. And you'll see that survival, or mortality, whatever way you want to look at it, was lower for the smaller fish than it was the larger fish. It's actually surprisingly pretty good for the larger fish. And if you look at the relative weight, that's the time of draining. They stayed in pretty good condition. I think that perhaps with the smaller fish, we might have put just a few too many in the ponds. And then the change in relative weight on the far right is, instead of saying the relative weight as we stock the fish, this is the change in relative weight. So the smaller fish, they lost a little, they went down in condition. However, like the flatheads, they were well above 100. We had some really robust flatheads, and so that might not be too indicative of a drop in relative weight. I think that just the 4 fish that perished were probably very rotund fish. DO throughout our trials was between 4 and 12, and the sampling temperature that we went for was MDC typically samples between 55 degrees Fahrenheit and 80 degrees Fahrenheit, so we're trying to sample within that window. Like Zach, we had a lot of zeros and highly variable data, so we used the zero-inflated negative binomial regression, and this is good for over-dispersed data. It models zeros or unsuccessful trials as kind of an independent logistic process, and we had a significant interaction between small blue catfish and the 1530 waveform, and so we modeled by these 4 different species and length categories. And then there's an oversimplified version of the model to just show that we included water temperature, waveform power, and then a random effect for pond. So these are just some of the plots of the data, and then the conditional model output, which is modeling catchability up in the top of the figure. So we had 31 trials for small blue catfish, and 29% were successful, at least one fish surfaced. You can see, so the power came up as significant, so reducing the power reduced catchability. And so here we have catchability on the y-axis, the two waveforms on the x-axis, and there's two facets. The blue is at the power, and the yellow is below the power. So you can see that with 810 for small blue catfish, we really struggled to get fish to come up. It's all highly variable, but with 1530 we had much better luck. And a mean estimate of catchability for at the power 1530 was about 6.5% for small blues. Now big blues was a whole different story, and we actually only had 3 fish in our 19 trials that even surfaced. So the differences in the mean values that you're seeing is really related to the pond, 1 out of 24 versus 1 out of 26 fish in the pond surfacing. We didn't have enough fish surfacing to get convergence in our model on any sort of estimate. So highly variable data. This is the small flathead catfish. None of the covariates came up as significantly influencing catchability. We had much higher success with our flatheads across both of them, with about more than 50% of the trials being successful fish surfacing. But if you kind of focus here, if power is not significant, we're not overpowering fish, then it's best to probably focus on the at the power of the blue, where estimates of catchability is about 3%, because we're not going to tell managers to reduce power outputs in the large reservoirs. That was strictly just something that we were evaluating in the ponds. And then for large flatheads, we had temperature pop-ups, so increased temperature, reduced catchability in this model, and then reduced power settings, decreased catchability as well. We had a lot of success, and maybe some size selectivity with larger flatheads. Again, if you focus on the blue, you'll see it's 6 to 8% for large flatheads, contrasted with maybe 3% for the small flatheads. So there's a zero inflated component to those models, and they would suggest that there's a relationship between water temperature, increasing water temperature, and increased likelihood of zeros. Unfortunately, because we only had one field season in the spring of 2019, this was highly correlated. So as water temperatures increasing throughout the spring, we're also cumulative shocking attempts on these ponds that we shocked 9 to 10 times was also going. So it's difficult to tease that out. Was it temperature, or was it just shocking these ponds over and over again? So we took a subset of the data based on a cold water sampling group that NDC uses. In this temperature group, you can see from the correlation of 0.5, a little less correlated, and it's because as temperatures were increasing, we had some rain events that dropped temperature while we were still shocking the ponds. And we found similar trends in the data, except now temperature was no longer significant for large flatheads, but that's something that we're going to look into a little bit more. As I mentioned, we did some electrical field mapping of the boat on Truman Lake, NBC boat. This is all done at about 1.5 foot depth, so about where the anodes would lay in the water column. And this is the capture-prone response thresholds to elicit these responses from the first phase of the study. So for blue catfish, flathead catfish, it's almost 0.2 of a volt per centimeter will elicit immobilization in that tank trial. But what's most interesting about this is based on our field mapping. As you can see, when you get to about 20 feet off the bow of the boat, you're not even really hitting that twitch threshold anymore. But as we all know, fish are coming up hundreds of feet from the boat. So after about 15, 20 feet, it's incredibly small field intensities. And then what I think is particularly interesting about the ponds is whether you're sitting over a channel or not, and I wondered if maybe fish that are right underneath the boat, something's getting triggered in them and they're kind of losing orientation and swimming out and their swim bladder's inflating or something like that. But fish in adjacent ponds were coming up shocked, and those fish are feeling maybe 1 millivolt per centimeter, which I don't even know if you could feel with your hand in the water. And they were never close to the boat at all. So that was kind of just an interesting observation. And then this is kind of squeezed out from the drone footage, but as most of you know, minute and a half. We had a minute and a half for at the power with 1530. With flathead catfish, where we had 6 trials, these are all successful trials, obviously, but the 810 waveform, it took a little longer for flatheads to come up. Didn't see that with blue catfish, but it's also really variable. We only had 2 times that blue catfish surfaced with the 810 waveform. And then the distance, this is mostly important to just reiterate that point that our average distances were 102 feet or 64 feet between the species. Well, either one of those is still maybe even sub 1 millivolt per centimeter. So it's almost nothing that's getting these fish to come up. I mentioned before, and I'll just touch briefly on it, that we tried some State Fair large aquarium shocking, and we also tried net pen trial, and we were unsuccessful getting any fish to surface in the aquarium trial, but it was also maybe the fish were stressed out, and we did this in summertime. And then our net pen trials, we had a boat approach from a long distance. We had a rangefinder and a voltage gradient probe and a large pen that we were sitting over, and as the boat would approach at the power goal, we could read the voltage gradient, and we could tell the distance from the boat, and we just watched the fish, and we got all the way up onto the net pen, and the fish never did anything. So overall, based on what we saw in the ponds off this one field season, we think that I was really surprised with the UAV footage, how crisp and clear it can be, especially for just counting fish. And as technology improves, maybe even measuring and counting fish might be a useful tool to avoid dip net selectivity or something like that. We recommend that catfish managers, most are already using 15 pulses per second, but based on our data, perhaps if you are sampling both species, probably just go ahead and use 1530 for both. Maybe some size selectivity between the small and large flatheads. We didn't see it with blue catfish, but it still might be present. And then mean catchability, it kind of is right in line with past research, 0 to 10% variable. So I'd like to thank all of the people that helped me, my committee member, Dr. Chris Weichel, for statistical support, my awesome field technicians, and then everybody at MDC that was always so willing to lend a helping hand and try all these different things. Any questions?
We got time for questions?
Did you see any difference in your rest times? You said you used 3 to 5 days rest between shocking intervals. Did you see anything in there at all?
No.
3 days was adequate?
Well, in the aquarium trials too, of course it's different, but within 2 hours, they kind of get the same threshold. And there's some research that was done on like the Lake Michigan and the Great Lakes that came out like a year ago that said, as far as estimating fish community size structure assemblage, that after I think it was 2 to 3 hours, their estimates were comparable. But with the 3 to 5 hour rest time, one thing that's different about this, like compared to shocking bass or panfish or something like that, these fish, yeah, they're surfacing and they're getting shocked, but it's nowhere near approaching a level that could cause injury. Yes, the fish could get used to hearing a boat come into the pond or something like that, which we can't really control for, but we're not hitting the fish with 0.2 volts per centimeter every 3 days. And so that's maybe another thing to think about in this case.
Any more questions? Okay, thanks.